to the seminar of today. The topic of the seminar is the dramatic transition in atmospheric boundary layer turbulence structure from neutral towards convective and the development of large-scale rolls. So the speaker of today is James G. Brasseur, and he's currently research professor of aerospace engineering science at the University of Colorado Boulder. After 27 years as professor of mechanical engineering, biomedical engineering, and mathematics at the Pennsylvania State University, where he's emeritus professor. He's a fluid analyst with extensive expertise in two general research. Turbulence physics, theory and simulation, and modeling within the large-eddy simulation framework, with application to fundamental nonlinear dynamics, atmospheric turbulence, wind turbine, aerodynamics, and turbulent combustion. And the second field of general research is fluid and solid mechanics integrated within physiology and function of the gastrointestinal tract, and drug delivery within the GI tract, including dissolution, transport, and absorption. He has served on governing boards of the American Physical Society, the APS Division of Fluid Dynamics, and two medical societies. He was president of dysphagia research.
Dysphagia.
Sorry. Dysphagia research society, medical society, and was founding chair of the APS topical group on the physics of climate. He's a member of the John Hopkins Society of Scholars, and he's fellow of the American Physical Society through the division of fluid dynamics. In summer, we will be happy to welcome him at LMFL whenever sanitary conditions allow. So whoever wants to approach him for a discussion could do that in presence in Lille during summer if sanitary conditions are always safe. So thanks. It's with great pleasure that I introduce Professor Brasseur for his talk of today. Jim, I leave you the stage. I stop sharing my screen.
Okay.
And
thank you very much, Francesco. Appreciate it. All right, tell me when you can see my screen.
We see it.
Okay. All right. So I was just going to say that if anybody has a dying desire to interrupt and ask a question or make a comment, feel free to do so. Okay. So the title was already read, and this work was actually part of a large effort funded by the Department of Energy in the United States on wind turbine technology. Yeah, so I want to say that the person who I was working with on this and who did all the simulations was Balaji Jayaraman, who was research associate with me at Penn State. He then moved on to become a professor at the University of Oklahoma State. And he left there recently and is now at GE Global Research in Niskayuna, I think, in New York. But anyways, as I mentioned, this was part of a wind turbine project, and the idea was my interest in this project, and I was the head PI, and so the focus of the whole effort was really on interaction between atmospheric turbulence and wind turbine. And I'm still very much involved in that research with people at NREL and so on. But as part of that, part of the issue was modeling the interactions between what's called the mesoscale and the microscale, basically the weather motions that happen above the atmospheric boundary layer, which is the first kilometer or two near the surface. And that's the focus of today's talk. But the idea is that the changes in the structure of the turbulence will impact the loadings on the wind turbine and so on. So this was the motivation there. This is actually a really interesting picture that I found somewhere, I don't remember, but it's showing a wind farm with large-scale roll structure. The clouds are marking the structure of these large horizontal, highly elongated rolls. So we're going to talk about that. This is something well known in the micrometeorology community. I'm part of the micrometeorology community through the National Center for Atmospheric Research. I've been working with people like Chin-Ho Mong and Peter Sullivan for many years. Chin-Ho is now retired, Peter's still around. These are just a few papers that kind of show some history of what's leading to the talk today. And the talk today is the bottom one. It was just recently published in the Journal of Fluid Mechanics. So anybody who wants to see details that I can't present in this talk should go to this paper. And I should say that I'm hoping that this talk will excite the theoreticians and experimentalists who are listening to me to think about perhaps how to understand this kind of discovery that we made here. It's very interesting. I'm convinced that it's real, and I'll explain why. But I don't understand the mechanisms underlying it. I think it has broad importance to boundary layer function in general, structure in general. And I'm hoping that somebody might approach me and say, I have an idea for how we might figure out what the mechanisms are, what the physical mechanisms are. So, all right, so just a brief introduction to the atmospheric boundary layer, since this is not a micrometeorology crowd. So first let me put my, all right, which one of these buttons do I push to get the, no, that's obviously not it. Well, you can see my pointer, yeah? Can everybody see my pointer? Francesco?
Yes. Yeah, we can see it.
Okay, anyway, so the atmosphere, of course, is composed of these layers. They're relatively thin compared to the size of the Earth. But the lowest part of the troposphere is where most of the weather happens that we experience. And the lowest part of the troposphere is the atmospheric boundary layer. It's capped by a capping inversion. So for example, this is measurements from radiosondes of potential temperature at different heights, just lifting up into the atmosphere. And you can see this transition. This is typical in the daytime boundary layer, where there's a sudden increase in the potential temperature. This is a stabilization layer. It's an inversion layer. And it keeps the three-dimensional turbulent structure confined within this lower 1 to 2 kilometers. In the morning, it starts at a few hundred meters and then grows throughout the day and reaches a peak at around noon, 2 o'clock in the afternoon, something like that, and then starts to collapse in the summertime, perhaps around 4 or 5 o'clock, and then collapses towards the nighttime boundary layer, which is a very different kind of boundary layer. This is the one that I will talk about. It's the one that's perhaps most relevant to engineering boundary layers. It's very much like a canonical engineering boundary layer, at least in the middle of the day. Except that it has buoyancy as well as shear, and that's the issue that I'm going to discuss. So just a few key issues here. Okay, so I already mentioned potential temperature, which measures non-adiabatic changes in temperature, or it removes non-adiabatic changes in temperature, and it's driven by a surface heat flux from solar heating at the ground, and then it's driven by shear due to a geostrophic wind or mesoscale wind. I tend to think of this more now as mesoscale wind, because our current research is really studying the non-equilibrium boundary layer, where the geostrophic wind and the mesoscale wind are not the same. But this boundary layer that we're discussing today, these are the same. Mesoscale wind and geostrophic wind are the same. So by canonical, what I mean is that the boundary layer is in equilibrium. Nothing is ever truly in equilibrium, so quasi-equilibrium, which implies quasi-stationary. And that's an issue that we'll discuss. Horizontal homogeneity is a reasonable approximation over regions that are relatively flat, like the middle part of the United States, and with homogeneous roughness elements, which can be approximated in the middle of the United States. There's some famous experiments that took place, for example, in Kansas and Minnesota and so on, where these were approximately the case. The surface heating starts at sunrise, of course, and reaches a peak somewhere in the middle of the day and then goes back to zero. And in fact, the flux, this is flux of internal energy or temperature, either into the atmosphere, so it's positive into the atmosphere, but after sunset it goes negative, and energy is actually taken out of the turbulent boundary layer rather than being put in. But it's this daytime process that we're really focusing on here. Homogeneity means, of course, that we're not in these strong time-dependent regions. We're up in this part of the daytime boundary layer during periods where the winds are relatively steady, and so that the boundary layer can be regarded as quasi-equilibrium. And like I say, there's validation for that statement. These aren't just words. This is an old issue. This boundary layer has been studied for decades now, so it's well known, especially in the micrometeorology community. As I mentioned, the issue is the interaction between buoyancy-driven motions, where turbulence is generated in the vertical fluctuations from buoyancy, and horizontally driven turbulent motions from shear production. And it's the interaction between those two that is sort of the focus of this discussion today. So here I'm just showing with some engineering simulations the sort of two classes of boundary layer, the purely buoyancy-driven boundary layer with no shear, which develops these convective eddy motions, but no horizontal motions. This is a visualization of a real buoyancy-driven flow. We're all very familiar with this, and this is a DNS of a homogeneous buoyancy-driven flow. And then the neutral, purely shear-driven boundary layer that we're all familiar with, the canonical boundary layer that we're all familiar with. And this is the homogeneous shear flow version of that. So these studies are independently trying to understand the interaction between mean shear, for example, and the generation of turbulence, the structure of the flow, et cetera, et cetera. And these same thing, but due to buoyancy-driven flows, which drive the vertical fluctuations, shear drives the horizontal fluctuations. Some of the key length scales that are important and that need to be understood for this talk, the boundary layer height, since there's this inversion layer at the top of the boundary layer, the canonical boundary layer, that maintains the three-dimensional turbulence fluctuations below. It's kind of a soft lid, as it were, but the height, the average height is called ZI, where I stands for inversion layer. Z is the vertical direction in all of this discussion. And the Obukhov length scale is a length scale that characterizes the turbulence production by shear through the friction velocity, which I'm going to use U star for. It's the symbols used in the micrometeorology community rather than U tau, and buoyancy-driven turbulence. So this length scale L is negative when the boundary layer is globally unstable, which is the daytime boundary layer, because of the flux into the boundary layer, so it's negative. So I put negative signs to make this a positive number, and the negative L then characterizes the separation between the part of the boundary layer where shear production is larger than buoyancy production and where buoyancy production is larger than shear production, so that when this number goes to infinity, then it's a neutral boundary layer. And when this number goes to zero, it's a fully convective boundary layer. So we think in terms of the ratio of the boundary layer depth to this Obukhov length scale with this minus sign put in front, where if this ratio is very large compared to 1, then it's convectively driven with very little effects of shear turbulence production. If it's very small compared to 1, then it's a neutral boundary layer. In principle, when it's 0, it's a neutral boundary layer. In fact, that's going to be the main point of today's discussion. And then we usually think in terms of what we call moderately convective boundary layer, where convection is really important, but shear is also really important. So this is where this ratio of scales is on the order of, say, 1 to 10, something like that. All right, so these are important, and the global stability is sort of the key to what I'm discussing today. So let's talk about sort of the, so I'm not going to really discuss this convective case here. I'm really discussing the transition from a shear-driven boundary layer to a moderately convective boundary layer. So this would be the shear-driven boundary layer where this stability parameter is 0. This is showing horizontal fluctuations. It looks very much like what we're used to in the engineering community. The low speed streaks are blue; those are the negative, and the positive are red. So this is the picture that we're all familiar with of coherent structure near the surface, in the surface layer, with low speed streaks interdispersed between high speed streaks, where the high speed streaks are less coherent than the low speed streaks, and so on. These are really important in what I'm going to be discussing, partly because in the neutral boundary layer, the vertical fluctuations, which are shown by these red isosurfaces here. By the way, this is a large-eddy simulation of an atmospheric boundary layer simulation, 3 kilometers on the side, and a couple kilometers in the vertical. But anyway, these red dots then indicate the concentrations of vertical fluctuations. They're relatively incoherent looking, and they're not correlated with the streaks below in a well-defined sense. On the other hand, when you add some heating from below and turn it into the moderately convective. By the way, I should also mention that the daytime boundary layer is more like this, and that's going to be one of the takeaways from this talk, that this is really what the daytime boundary layer looks like, barring storms and all of that, which of course changes the whole thing. But in the moderately convective case, where this number might be 8, for example, you still see the low speed streaks, but the high speed streaks become blobbier, less coherent, less well organized, and so on. But the point is that these low speed streaks are still there. They will eventually go away when the stability parameter goes to very large numbers, and it becomes a purely buoyancy-driven flow. When the flux is now introduced and you get this moderately convective boundary layer, then the vertical fluctuations really change their structure dramatically. For one thing, you're now generating vertical fluctuations, but the coherent structure now is very much tied to the low speed streaks below. So this is a big difference. This was discussed in this paper by myself and Samir Khan in 1998. And we make the point there, we make the argument there that the low speed streaks are where temperature fluctuations tend to concentrate, and this generates concentrations of turbulence generation due to buoyancy. So we call them the seeds, and it's very well correlated. You can see this is a very robust thing. If you do these kinds of simulations and look at the relationship between the vertical fluctuations and the horizontal fluctuations, they're very well correlated with the low speed streaks. So I'll come back to this in today's discussion. These are just some pictures that came from this 1998 paper with Samir, where when you take the stability parameter to values that are large enough, then you get this very strong coherent updraft motion. So the reds are updrafts and the blues are downdrafts. This is the vertical fluctuations. This is near the surface, and this is halfway into the boundary layer. And you can see the imprints near the surface, but these horizontal, these very strong coherent updrafts are part of this large-scale roll structure that is studied quite a lot in the meteorology, or has been studied quite a lot in meteorology, going back to Lamone's work in '73, and Tammy Weckworth has written some nice review papers on this. So this is something that has been observed in the meteorology community for a long time. You can, like I mentioned before, in certain conditions, you can see these kind of parallel rows of clouds, and they sit on top of these rolls because moisture is being driven into the top of the boundary layer, and then it condenses into these rolls. And these go for many boundary layer depths, tens of boundary layer depths in the horizontal. They're very coherent, but the mechanisms that create them are not fully understood, and this talk will have something to say about that. All right, so this is what we're doing in this discussion. We're going from the neutral case, which is this one that I showed, to the moderately convective case, which is this one that I showed. But we're doing it in a very systematic way, where I should mention that since it's an equilibrium boundary layer, it's really characterized by, it turns out, only the stability parameter. The Reynolds numbers are so high, and I also neglected to mention that we're talking about rough surface boundary layers. The atmospheric boundary layer is a rough surface boundary layer, so you don't have a viscous layer near the surface, but the behavior outside the viscous layer is very much the same. But the point is that this transition process, the question is, does it happen gradually, or is there some interesting transition stuff that goes on? And when we started this work, Balaji and I started this work several years ago. I asked Balaji to do this just in sort of a rough way at the beginning, to see how this transition happens. I assumed it was going to be smooth. And I just wanted to see just how smooth, and sort of like where did the transition between the neutral and the moderately convective, what stability states was that really high? Everybody assumed it was order 1, but it was just an assumption and so on. But we were surprised. It turns out it's much more interesting than that. And after many years of work, we now have this interesting study to discuss today. So we use large eddy simulation. Which is an issue because you have to be very careful to get things right when you do it on the computer. But the wonderful advantage of the computer is that you can create truly quasi-equilibrium boundary layers. In the field, it's difficult. Certainly it has been done, and there's some very important studies that have been done, like the Kansas experiments and so on, that have been done. But it's not as clear in the true atmosphere as on the computer. All right, so the simulations, without going into great detail, these have been done by decades, by a number of people, including myself. So they're well known. But the code that we use is pseudospectral in the horizontal and finite difference in the vertical, second order finite difference in the vertical. This is actually a code that originated with Chin Ho Meng and then went through Peter Sullivan and then went through us. And I also worked with John Wingard for many years on this stuff, so one of his students and so on. So this is a well-evolved code that we used. It uses a rough surface boundary condition, which is an issue that I don't have time to go into. It's a whole nother topic that is worth a couple talks and so on. And one specifies a geostrophic wind above the boundary layer and a surface heat flux at the surface. And it's the combination of the geostrophic wind and the surface heat flux that determines the stability state of this boundary layer. It assumes horizontal homogeneity of everything, basically, including the roughness elements and the turbulence structure and so on. The horizontal domain has to be large enough to capture the integral scale eddies in the horizontal, and we understand what that is. 5 kilometers is sort of a typical size. There are arguments for larger horizontal domains when convection is there, and I'll come back to that again as well. So we solve the filtered Navier-Stokes equations, of course. Everybody's familiar with that. And the subfilter scale stress model is the eddy viscosity type. One equation, eddy viscosity type. Again, this is a model that we've been using for decades now that originated, again, with Chin Ho Meng at NCAR. We solved the equation for potential temperature, and it has a subfilter scale flux term. These are the terms that need to be modeled, and it is also modeled with an eddy diffusivity model. So this is all standard stuff. We can discuss it if you want, but this has been in the literature for quite some time now, so it's very well known. We use the Boussinesq approximation so that the buoyancy term is modeled, is approximated, linearized according to the Boussinesq approximation, and the local divergence of the velocity is taken to be 0, so it's locally incompressible, but globally density and temperature varying. There's also an important term that is due to the Coriolis, since we're in a rotating frame of reference on the Earth. So this is a Coriolis term, and that has the effect of turning the direction of the mean velocity away from the direction of the geostrophic wind from the surface up into the boundary layer. This is all sort of standard, well-known stuff that people who do this kind of work understand very well. This shows the grid that we used. This is actually a grid that was not arbitrary. I'll talk about that in a second. You de-alias using the standard 2/3 rule in the horizontal direction. Let's see. Okay, so boundary condition at the ground is an important issue that I don't have time to go into in detail, but the basic boundary condition was presented in this classic 1984 paper by Chin-Ho Meng. It's, you know, some differences nowadays, but this is pretty much same model with some minor differences to it. Roughness height of 0.1 meter. Okay, I don't have time to talk about every little thing, so I'm going to move on. All right, so things that are important, in order to establish the capping inversion, you establish it with the initial potential temperature profile. This sets the initial capping inversion height. You generally set it at a few hundred meters, and then it'll grow with time as the simulation proceeds. This has to spin up like any simulation, any turbulence simulation, and the spin up process is what leads eventually to the quasi-stationary state. In order to decide whether you've arrived at quasi-stationary, you compare the rate of increase of the capping inversion with the characteristic vertical velocity scale, W star. I'll show that in a second. This has to be small compared to 1 in order to argue that it is quasi-stationary. So we check that to make sure that it is. I already mentioned that we use the one equation eddy viscosity model. All right, other important issues have to do with, okay, so what we're doing is, since the boundary layer is characterized by the ratio of the capping inversion height to the Obukhov length scale, that's the only parameter required. Since Reynolds number is so large, it basically is no longer a relevant parameter in these simulations. In fact, we don't even have the viscous term in these simulations because the Reynolds number is large enough that it has no impact. But at any rate, you can do this one of two ways. You can either modify the geostrophic wind above the boundary layer, keeping the surface heat flux constant, or you can modify the surface heat flux, keeping the geostrophic wind, or you can modify both simultaneously. We want to do this very carefully in a way that we don't have to alter the grid of our computer simulations, because when you alter the grid, if you did that in the middle of the simulations, then it might introduce some artifacts that you don't want to introduce, because then you have to understand whether or not they're impacting the dynamics and so on, especially for this study where we show some interesting critical phenomena. So what we do is we hold the geostrophic wind constant and we systematically increase heating. So you kind of might think of this as the surface heating in the morning at sunrise. So the numbers we actually use in this study, which change the stability parameter from the neutral case to something like 3.84, it really corresponds to the very early morning. Having said that, the very early morning is not an equilibrium boundary layer. The equilibrium boundary layer is up there, but still, in terms of the stability state, it corresponds to the very early morning, very small levels of surface heat flux compared to the peak surface heat flux, which occurs in the middle of the day. So we're talking about small additions, but very carefully, systematically increased over this range in order to increase the stability. The capping inversion was important. We wanted to have a strong, the stronger the capping inversion is, the slower it grows. So that's good, but you don't want a capping inversion that's so strong that it's not physical. So what we did an analysis. We looked in the literature, did quite a lot of looking in the literature and talking with my colleagues and getting data and looking at it to decide what sort of normal capping inversion strengths. And we chose capping inversion strengths that are within the normal range, but are on the high side of normal in order to maintain this rate to be small compared to W star. So again, we're trying to be very careful. There's this, this carefulness is, I should say that we were trying to be very careful, partly because we were trying to be very careful and partly because the reviewers demanded that we be even more careful than we thought we already had. So we had to kind of, we actually did these simulations twice. And the reason was because of this thing called the Overshoot. People who do large eddy simulations of the high Reynolds number turbulent boundary layer know that there's this problem that's been around for decades that we talk about, and we call it the Overshoot. And what it is that the mean velocity gradient, the shear rate in the vertical, non-dimensionalized according to law of the wall for the inertial law of the wall layer, it's been known for a long time, the large eddy simulation predicts this, what they call the overshoot. This is supposed to be, in the neutral boundary layer, this is supposed to be constant over the surface layer, this region right here. And this is the typical profile that you get. In fact, most of the papers of the atmospheric boundary layer really have this kind of a profile in them. There are a number of groups who are trying to understand what was causing this and how to fix it and so on. And we wrote this paper in 2010 that we feel like explains the basic mechanisms. I don't want to talk about this in this talk. I just want to say that we used the procedure that we developed in 2010 in order to get rid of the overshoot. You get rid of the overshoot by adjusting the grid together with the parameter that goes into the subgrid model. In this case, we held the subgrid model parameter fixed, and we varied systematically the grid to move it away from, get rid of this overshoot and turn it into a more reasonable law of the wall consistent velocity profile. This is for the neutral case, and this is like the strongest roll state that we'll talk about, and we did it for all of our simulations. And this actually meant that we submitted the paper twice to JFM. The first time, the reviewer said, no, you've got to be more careful near the surface. So we literally redid the whole set of simulations, and that's what we now have published. I will say that the primary results actually got better when we got rid of the overshoot, and which suggested that the overshoot, which this paper explains, the overshoot is due to spurious frictional effects that come from the model and so on, that you minimize those frictional effects, and that means the frictional effects are actually covering up this critical state that we're going to talk about in a second. I already mentioned about quasi-stationarity. So this is all the care. We also studied grid resolution and domain. Again, I don't have time to go into these studies, but we found that if you increase the resolution, we did this for a few of the simulation, the results actually got sharper. And if you change the domain, basically the results didn't change, but we did, because the horizontal roll state has strong correlations that go over tens of kilometers for the horizontal fluctuations. It's pretty much impossible to create a domain in the horizontal that captures those, because it would be too large. You couldn't fit it into the computer. But this is true with everybody. It's just the nature of these kinds of simulations. But it didn't impact the basic results that I'm going to talk about today. Okay, so this is a list of all the simulations that we did, and I have circled. So this is the stability parameter, the surface heat flux, the cap and inversion height, and these are the four that are going to be talked about. Mostly the neutral state. This is a critical state that we're going to talk about. This is we call the maximum coherent state that is associated with the large scale rolls, and then this is the highest that we calculated. And you can see that the surface heat flux was really quite small, even at the highest stability state. It's still very small compared to the peak in the daytime boundary layer, and you can see the cap and inversion heights here. Okay, again, just sort of just giving you the background. So here I plot a number of quantities as a function of stability state going from neutral 0 to the highest stability state, which is like 3.84. The cap and inversion height is dependent on this, because surface heat flux creates stronger buoyancy, which pushes the cap and inversion. So this is the cap and inversion height during the period of analysis, which is this quasi-equilibrium period, and it does grow, but not too much with over this range of stability states. Of course, the Obukhov length scale changes dramatically, as does W star. These are related to each other, and this is the friction velocity. So this is the U star. This is the characteristic shear velocity scale in the surface layer, and this is the characteristic vertical velocity scale in the mixed layer, above the surface layer in the convective case. The friction surface friction stress is roughly constant over this entire range, but W star, the characteristic vertical velocity scale, is changing quite dramatically along with the Obukhov length scale. Okay, so let's now get into the results. So if you ask yourself, Okay, those who, I mean, we're in engineering, we're used to the neutral boundary layer. That's mostly what we study in engineering. And we know about these streaks. We know that they're very coherent. We know that they're highly elongated and so on. And if you just thought about it briefly and you said, well, what would happen if you took a neutral boundary layer and you started heating at the bottom, just a little bit of heating at the bottom? What would happen to the coherence lengths of these streaks? And you would think, well, these streaks are being generated by interaction between mean shear and turbulence fluctuations. This is well known. There's a lot of work done on underlying that statement. So therefore, at least I argued, and this is what I certainly expected when we started this work, that you add any amount of surface heating and it's going to disrupt the horizontal coherence and the streamwise direction of these streaks. And you would expect the coherence length to drop. You'd expect something like this. So if this is the coherence length of the horizontal fluctuations in the horizontal direction, non-dimensionalized on the boundary layer depth, you would think that as soon as you start to add heating, and one thing I did want to point out is that the heating Q naught is, I have that? I thought I had that. This is kind of an important point. Yeah, here it is. The stability parameter is approximately linear with surface heating. So as we're going to be writing everything in terms of the stability parameter, but you can kind of think of this as linearly proportional to the surface heat flux. So going back then to this point here is, as you add surface heat flux to the neutral boundary layer more and more, qualitatively, you would expect that the horizontal coherence length of near the surface would drop in the surface layer. You disrupt the coherence, and this is what I expected. It was surprised to find that that's not what actually happened. This is what happened, and this is kind of like, whoa, kind of. You don't get this drop until this particular critical state is reached. Before that, there's relatively little change. There's definitely changes going on here, but then suddenly around this critical state, so you're adding a little bit more heat, a little bit more heat, a little bit more heat. The boundary layer is changing its horizontal structure of the horizontal fluctuations a little bit, and then as you approach this peak right here, suddenly these guys increase. That means the horizontal lengths of the horizontal fluctuations, the horizontal coherence lengths is dramatically increased. I mean, we're talking about numbers going from like between 0.5 and 1 to numbers like around 2. So this is a big change, factors of 2 and more change in the horizontal structure of these coherent elements near the surface. But it's not just near the surface. So 0.01 is the black line, that's near the surface. 0.7 is up near the top of the boundary layer, near the capping inversion. So it's actually over the entire structure. In fact, the effect is even stronger outside the surface layer than it is in the surface layer, but it's everywhere. So this was quite a surprise. This is what we expected to find, and you do find it, but it's delayed until there's the boundary layer has changed. You don't get this reduction in coherence length until the boundary layer has become a different boundary layer than the neutral boundary layer. That I think is just fascinating. I don't understand the mechanisms, and I'm hoping that people like Srini and Francesco and people who do experiments can maybe think about doing some experiments. But I want to talk about now what we understand. So this was the initial result. It's much more refined than it was when we first got it. But now that we've refined it, it's a pretty strong result. And we find that there's this transition from the neutral state to this new state, which we're calling a critical state. There's some kind of a critical phenomenon going on here. And this is a different boundary layer. And then the boundary layer evolves differently as you continue to add heat to the surface of the boundary layer than it did from the neutral state up to this point. All right, so what else can we say about this? Well, we can say that this transition happens at this critical stability state, about 0.4, which is pretty small because up to this time, most of us assumed that, pretty much between 0 and somewhere approaching 1, that this is essentially a neutral-like boundary layer. But clearly it's not. it's a very different kind of a boundary layer suddenly at this point. It's only neutral-like, and we've analyzed it. It stays roughly neutral-like in this region, but as you approach this point, it's very much not. It's a very different boundary layer. And what's different about it is not what you would think. The streaks have actually gotten more coherent, not less coherent, and they've elongated. So you end up with you're starting with a boundary layer at this point that has longer coherent, stronger streaks than they did in the neutral state, which is baffling. How does that happen? If you look at the vertical velocity now, so this is the horizontal coherence length of the vertical fluctuations. It has an interesting behavior as well that kind of goes along with this one, but has some important differences. You do notice that the coherence length, this horizontal coherence length, doesn't really change, even less. The horizontal coherence length of the horizontal fluctuations change more than of the vertical fluctuations, which is surprising as well, since we're adding heat flux from the surface, which, if anything, they're generating vertical fluctuations. But then suddenly around this critical state, there's this tremendous growth. In a relative sense, it's even more of a growth in the horizontal than in the horizontal fluctuations. The vertical fluctuations actually extend more in the horizontal than the horizontal fluctuations did. But whereas in the horizontal fluctuations, once you go beyond this critical stability state, the coherence length systematically decreases over the entire boundary layer. In the vertical fluctuations, they continue to grow. So, naively, you might think that if you add heat flux at the surface, that at first maybe you don't generate strong buoyancy-driven eddies, but then at some point you do, and then these eddies would just grow in length. Well, that growth doesn't start until this critical state. It does happen, but it doesn't start until this critical state, and then it reaches peak coherence in the vertical at a stability state of around 1. And this is what we call the maximally coherent stability state. And we will argue that this is what is associated with the strongest, most coherent large-scale roll state of the boundary layer, this large scale. And by the way, I should say that these large-scale rolls are related to what the engineering community is calling very large-scale structures in the boundary layer. This has been known in the meteorology community for a long time, before it sort of became a thing in our community. But these are manifestations of horizontal fluctuations interacting with the vertical fluctations due to buoyancy interacting with the horizontal fluctuations and creating these very strong horizontally coherent updrafts, which are part of the roll structure itself. All right, so now if you put this other state on here, so we call this the critical state, and we call this the maximally coherent state, and you put that other line back onto the horizontal coherence lengths of the horizontal fluctuations, then you do see that there's some slight impact of this roll state, but it's much more prominent in the vertical fluctuations. All right, so let's look at this a little bit more. So let me just kind of summarize what we know to this point. What we know to this point is that as heat is added up to this critical state, the horizontal coherence length of both the horizontal and the vertical fluctuations is not changing very much. And then suddenly, dramatically, the horizontal coherence lengths increase by factors of about 2 or so in the horizontal fluctuations, but by factors of more than 2, 3, and 4 in the vertical fluctuations, but it's the horizontal coherence length. So basically what's happening is that these relatively incoherent vertical fluctuations are now amalgamating and they're aligning themselves with the low speed streaks underneath. This effect that I mentioned earlier that we presented in this 1998 paper with Samir Khanna, it seems as if this happens, but it doesn't happen until this critical state is reached. And now you get a strong coupling between the surface layer streaks below and the updrafts above, which then eventually turn into the large-scale roll structure, which has its maximum coherence at this state right here. So the dynamical structure, as well as the kinematic structure of the boundary layer, has changed at this critical state, which again is very interesting, I think. Right. So if you take the ratio then of the horizontal coherence length and the vertical to of the vertical fluctuations to the horizontal coherence length of the horizontal fluctuations, the ratio starts off very small. That's the neutral state. And then at this critical state, suddenly this ratio starts to grow. So this is, again, an indication that the dynamical evolution has suddenly changed. The boundary layer is a new boundary layer, and it evolves in response to surface heating. It now responds differently than it did pre-critical or subcritical. Supercritical is a different response than subcritical. And the ratio of these two scales, you would think that as this maximum coherent state is reached is when it would reach a peak, but in fact it doesn't. These are all different heights in the boundary layer, but they go up. This ratio goes up rapidly. The horizontal this is again horizontal coherence length of the vertical fluctuations is growing relative to the streaks. This is the streaks below here, and they become order 1 in the middle of the boundary layer and the mixed layer at roughly 3, at a stability state of roughly 3. And then they start to decrease. So we define, we characterize this as kind of the beginning of what you might call the moderately convective state, whereas this would be a transition to the moderately convective state. The roll structure is breaking down and so on. And then this would continue into the moderately convective state before it goes into the fully convective state. By the way, I should also mention that the transition from the moderately convective to the fully convective state was studied by Marcello Cimecchi shoot, oh, he's going to kill me for forgetting his name. Anyway, his student at the time, he's now a professor. Anyway, so okay, so this is showing that the topology of the vertical updrafts and the horizontal updrafts has changed dramatically from these the critical state to this maximum coherent state, in which the horizontal fluctuation, the horizontal coherence of the vertical fluctuations is now of order the coherence length of the horizontal fluctuations, whereas it wasn't before. It was much smaller before, and now it's of order. Okay, so you can kind of picture this boundary layer as growing in the horizontal, not in the vertical. That's what's really fascinating, is that the dramatic growth, even though you're injecting energy into the vertical fluctuations, the dramatic growth is really in the horizontal direction, not in the vertical direction. There is growth in the vertical direction. I'll come to that in a minute, but let's continue on. So you can look at these data in a very enlightening way by, instead of plotting at different heights, as a function of stability state, we plot across the boundary layer at different stability states. So this is Z over Zi, that's the top of the boundary layer, and this is the neutral state. The black is the neutral state, and this is the horizontal coherence length of horizontal fluctuations. That's what it looks like. As the stability state increases, as the boundary layer becomes more unstable, there's slow horizontal growth. Until you get to roughly 0.3, and then between 0.3 and about 0.43, there's this explosion of horizontal extension of the coherence lengths. It just jumps, but it doesn't just jump near the surface. In fact, it jumps mostly at the lower part of the mixed layer, but it's a very strong effect in the mixed layer. So it's an effect over the entire boundary. It's a global effect, not just a local effect. The entire structure of the boundary layer has changed. And again, I want to emphasize that at this critical state, the surface heat flux is very little. We've hardly added any heat at all. All right, so the implication then is that since it takes very little heating to change the structure of the boundary layer, and this is happening in the early morning when the boundary layer comes up, basically the atmospheric boundary layer during the day is not a neutral boundary layer. It's very much not a neutral boundary layer. And this is important because it's often modeled. In fact, it's usually modeled. In the engineering community, like for wind turbine analysis and so on, it's always modeled as a neutral boundary layer. I've been making the case that it's not, and we need to do something better for applications of the boundary layer structure to other issues like wind turbine function, for example. All right, now what about the vertical fluctuations? So these are the horizontal. What about the vertical coherence length? These are the horizontal coherence lengths of the horizontal fluctuations and the vertical fluctuations. Here's the vertical coherence length of the horizontal, spanwise, and vertical fluctuations. So pointing in particular to the vertical, the green line here. So up to the critical state, there's very little growth, a little bit, but not too much. And then at the critical state, the slope changes and it starts to grow systematically till the maximum coherent state is reached. In which case it continues to grow until this, what I call the beginning of the moderately convective state, where it reaches a peak. So at this point, the vertical fluctuations are connecting the lower boundary layer to the upper boundary layer. They're communicating. There's strong communication between the lower and the upper boundary layer. But in this initial period, there's very little communication, and then the critical state initiates that growth in communication between the lower and the upper boundary layer. Also interesting is that the vertical coherence length of the horizontal fluctuations also increases a little bit up to the critical state, but then actually decreases after that and crosses over with the vertical coherence length of vertical fluctuations at about this maximum coherence state right here. But then the vertical coherence increases for vertical fluctuations and continues to slowly decrease into the moderately convective state for the horizontal fluctuations. So again, I'd like to emphasize that what this is telling us is that the critical state boundary layer is a totally different boundary layer from the neutral boundary layer, and the dynamical evolution with the addition of surface heating is also very different. Okay, so now going then beyond the critical state, looking at the coherence lengths through the entire boundary layer. So this is again the coherence in the horizontal of the horizontal fluctuations. So we've gone to the critical state here. The structure, these are visualizations that we're trying to tie to this statistical picture here. So this is so what we're plotting here is is a plane of isocontours of horizontal fluctuations superposed with these red dots, which are isosurfaces actually of vertical fluctuations. So in the neutral state, there's very little correlation between the updrafts and the streaks, but at the critical state, suddenly they're strongly correlated. And then this is the transition. They're starting to become correlated. But one of the important impacts of the critical state of transition is that now the surface layer streaks are very well correlated with the updrafts. And this, we argue, is basically the effect that Kana and I were discussing in 1998, except that it doesn't start until the critical state. And then this interaction becomes actually stronger in the transition from the critical state to what we call the dominant roll state or the maximum coherence state. So here's again this picture of coherence lengths of the horizontal fluctuations across the boundary layer. So we're now at this critical state, 0.433, and increasing to about 1. And this arrow shows what happens to the horizontal coherence length of horizontal fluctuations decreases, but it also changes the structure throughout the boundary layer. The decrease is stronger in the mixed layer and remains larger at the top of the boundary layer and closer to the surface layer. And this, we argue, is a result of the beginning of the formation of large-scale rolls. When the vertical fluctuations are now generated due to buoyancy, and I argue that until the critical state is reached, the fluctuations in temperature are more or less passive fluctuations, but now they become active fluctuations and they generate buoyancy-driven vertical motions. And these vertical motions have to go horizontal at the top of the surface layer. And I argue that that's what's generating this higher value of horizontal correlation in these fluctuations. So the structure has changed, and it's now become a different kind of a boundary layer again. Visually, if you look at this transition, then this relationship between the updrafts and the low speed streaks actually gets stronger. You can kind of see that visually, but also the vertical updrafts amalgamate more and more and become stronger and stronger and more coherent in the horizontal direction. I should mention that the reason why these are not in the streamline, this is the direction of the geostrophic wind, is because of the Coriolis force. So this is a Coriolis effect. But the idea here is that these correlations between low speed streaks and updrafts become stronger, and that correlation initiates in the critical state and becomes strongest at this dominant roll state, which now will show it breaks down after that slowly. All right, so here we're going then from this dominant roll state. So we argue that this is the state that the rolls have the strongest streamwise coherence and extend the farthest in the streamwise direction. You can see that they actually extend outside of the computational domain. I mentioned this earlier in the discussion. And they go tens of kilometers. So it's just not possible to create a horizontal domain that captures them in their entirety. But the coherence links, on the other hand, become of order the boundary layer depth. You can see 1 to 2 in here. So you can, we are capturing the coherence, the integral scale, but we're not capturing the coherence extends beyond the integral scale. Anyway, so as her surface heating, as you add more and more heating to the surface, this roll structure starts to become less coherent. It's still very much there. It hasn't gone away, and the relationship with the underlying streaks is still there, but it becomes systematically, it breaks down, and you can see it's broken down quite a lot here. And I argue that this is the beginning of what you might call the moderately convective state. All right. See, I haven't been keeping an eye on the time, and I always tend to go over here. So how much, where are we, Francesco?
So we're about 1 hour long. So.
Okay. So because I put this in and I said, well, I'm not going to show it if I go over time. So we'll go right to the conclusion slide. All right. So there's a lot more detail that's in the paper. But this is basically the summary of what I just discussed. The atmospheric boundary layer is strongly dependent on the global stability state, parameterized by the ratio of scales, the boundary layer depth to the Obukhov scale. The turbulent structure in the neutral state is entirely due to shear production, and that creates these elongated coherent structures near the surface, and the temperature is a passive scalar. Buoyancy generates vertical fluctuations, but there is this strong sensitivity between the heat addition and the horizontal fluctuations, even at low heating rates. So again, I want to emphasize this critical state is really low heating, and yet the horizontal structure of the shear-driven eddies is dramatically changed. How that happens, I don't know, but it's really interesting, and I would love to have somebody do some experiment to explain how it happens. There's this special transition state at around 1 that we call the maximum coherent state that's associated with the strongest large-scale atmospheric rolls. And this critical phenomenon, which is the most sort of important takeaway from this talk, at about 0.3 with very small increases in surface heat flux. But the roll structure doesn't, the formation, the process that generates the rolls doesn't initiate until the boundary layer has become this new boundary layer, this critical state. And then the other takeaway that in the true atmospheric boundary layer, a neutral, canonical, stationary, quasi-stationary atmospheric boundary layer does not exist. Certainly, you can argue that the neutral stability state exists, but it's not an equilibrium boundary layer. It's a very different kind of a boundary layer. All right, so that's it. I'm sorry I went over. I should have been paying more attention to the time.
Oh, no problem at all. And thank you for the very interesting and detailed talk. So I would like to open the stage for discussion. So whoever wants to ask a question, just feel free to unmute your mic and ask your question.
Good morning. Can you hear me?
Yes, yes, I do. Yes.
Good morning. Thank you for. We'll just put the video. So thank you for your very interesting talk. And I have two questions, in fact. The first one is related to the capping inversion layer 8. As I understand it, you controlled VI through the capping inversion temperature gradient. As I understand it, you controlled the capping inversion height using.
So are you asking how do we quantify the capping inversion height?
Yes, this is.
Quantify it. We actually look at
question, yes.
Okay, so let me go ahead and answer that. Then you can ask your next question.
Yeah.
We actually it can be quantified in different ways, but many of us use the vertical temperature flux profile. The vertical temperature flux reaches a well-defined minimum near the capping inversion. So that is all used as a definition of the capping inversion. And that's what.
And you were controlling it in your simulations so that to maintain the capping inversion inside your box?
Oh yes, yes. We're very, very careful. Again, we went to great extremes to be as careful as possible. So the computational domain was always a minimum of 2 times the capping inversion height, and it was used 3 times the capping inversion height.
Okay, so I was wondering if the capping inversion height would be affected by the transition you were mentioning before.
No, it's not.
Not? Okay.
I showed it's not at all. Let me just show you the picture that I showed earlier, the capping inversion height as a function right here. Here's the stability state.
Okay.
Inversion height. You can see it's a nice.
Okay, so it was maintained quite constant. In fact, okay, yeah, all right.
Right.
And it was without controlling it, or it was trying to control the temperature gradient.
Okay, well, the temperature evolves by itself. You start with an initial condition.
Okay.
The temperature is right, and then it evolves by itself. So. Yeah, and yeah. Anyway, I can go into more detail if you want, but it evolved. I think that's what you're asking, right?
Okay, all right. Well, we will maybe see each other during your visit at Lille, so it would be very interesting to discuss every of
yeah, maybe when I'm there, I can maybe give some discussion about atmospheric boundary layer stuff.
Right.
We can talk about that.
Right. And so my second question was related to a more general view. I was wondering if such structures and transitions associated with it could be observed in other cases where shear and buoyancy are interacting with each other, or is it related specifically to atmospheric boundary layer, or do you have an idea about this? Or
it's part of the reason why I'm giving this talk. I see no reason why it should be specific to the atmospheric boundary layer. I guess the more, the more relevant question is roughness required for this process to happen, or does it also happen in smooth wall boundary layer? That I think is an interesting question. I don't know the answer to it, but if it's a rough surface high Reynolds number boundary layer, it should. This says that it should, but of course, I would very much like to work with somebody to answer that kind of question. Yeah.
Okay. Thanks a lot.
Yeah. So I see there is someone else. So Giovanni Jacobello.
Yes, one question. Yes, I have one question.
Just a second, because there was someone else who, Giovanni Jacobello, who just raised his hand right now.
Oh, you want to raise the hand? Okay.
Yeah.
Okay, that was Giovanni.
Thanks. A quick question. It's more like a question and a curiosity. So my question is, this is really interesting. So thank you very much for the talk. And my question is, if you have looked at, say, other statistics, like, for example, quadrant analysis or conditional analysis on horizontal and vertical velocity, because it seems to me that there is an impact of this moderate flux on the, let's say, near wall cycle, so impact on ejection and sweeps mechanism. So perhaps there is a sort of feedback on this. So that's my question.
Yeah, it's a good one. We didn't do quadrant analysis, but we did, of course, look at standard statistics. And this was the slide that I jumped over. And the point that I was going to make, so this is the horizontal variance, vertical velocity variance, vertical heat flux. This is the production term in the turbulent kinetic energy equation. And this is the shear production term. So this is the buoyancy production term, shear production term. This Reynolds stress and vertical transport. Anyway, so if you just kind of visually look over these plots, and here's the critical state, here's the maximum coherent state, there are certainly changes that have happened, right? I mean, you can see this point here. In the vertical heat flux, not so much. There's just this gradual change. But these changes are overall milder than they are in the structure itself. I have to say that because we were focusing on applications to wind energy, I was really interested in the structure, and that's why we sort of focused on integral scale, and I'm glad we did, because the impacts are more clear in the integral scale structure than it is in the variances and so on. But you do see them. You can see here. Now you might think, for example, in turbulence production, right? You might think that the turbulence production would be dramatically impacted. And it is impacted, but not dramatically. It goes up somewhat, and then it just systematically comes down after that. Buoyancy production is just continuously rising. So you know, the quadrant analysis would fit under this picture here. So yeah, I mean, it would be interesting to go into it and find out whether the ejections and sweeps and so on have changed at this critical state. I expect they have, given this plot right here.
Yeah, and my second point is related to the question by my previous question of Thomas. Is more a curiosity by me. If you think that this kind of, let's say, transition could be exploited for some control strategies, even for other applications. Let's say, if you were able to control the heat flux at the surface, I mean, enhance or reduce the turbulence impact.
Yeah, I hadn't really thought about applications. I'm more fixated on what are the mechanisms at this point. Okay. But yeah, right.
Thank you very much.
Right, thanks.
Jim, if I could actually continue from that, can you hear me?
Yeah, I hear you, Christos.
Yeah, from what just happened, the last question. I've seen these plots here you don't have a correlation between the, I guess, theta prime is potential temperature fluctuation, and U prime, you don't have, is there a correlation between temperature fluctuations and the streamwise velocity fluctuations?
Well, I mean, there is, but it's not something that people generally focus on, because this is the production term. So generally people focus on the vertical flux rather than the horizontal flux. I haven't looked at it, and I don't think too many people have, really. Are you thinking that there could be that? Yeah, that's a good. No, I think, yeah.
If you have the Boussinesq forcing the equation, it is vertical. So if you write an equation for the Reynolds shear stress, you write an equation d by dt of u prime w prime, you will have the usual term that produces Reynolds shear stress, but you also have a new term which will be theta prime times u prime.
Yeah. Okay. Yeah, that's a good point.
Yeah, I don't know if there is I don't know if something happens there. Sorry.
No, I think you're right. It didn't occur to us. I wish you had brought this comment up a couple years ago, because then we would have looked at it. But we didn't. But it's a good point. It would be a good thing to look at. Unfortunately, this is over now. But maybe if somebody approaches me, we can get back into it.
Actually, a couple of years ago, I was visiting you. So, but we were up in the mountains, so we're doing other things. Anyway, thank you very much.
Okay, thanks, Christos.
Can I talk?
Yes, please go ahead.
Yes, my name is Bertrand Carissimo. I'm from Syria. And I was wondering, the way you presented is could be also seen as the diurnal evolution of the boundary layer, starting from a near nighttime to going in the morning. And my question is, have you tried to do this diurnal time evolution? Because we've also tried to do it ourselves, and we found that they have very different resolution requirements. Like the nighttime needs very small grid,
right.
and also that is there different phenomena going from this unstationary simulation?
Right. That's true. Everything you said is true. Do you want me to just elaborate on it, or do you have a question?
No, I was wondering if you try to do this unstationary, is it different just to do?
Yes. Well, I mean,
why did it increase the heat flux?
Yeah. Well, the nighttime boundary layer is a very different boundary layer from the daytime boundary layer. The heat flux is out of the boundary layer into the ground rather than out of the ground into the boundary layer. So it's a stabilizing boundary layer. It's also a highly non-stationary boundary layer. One of the reasons why I tend to focus a lot on the daytime boundary layer, part of it is because it's the turbulent, it's really turbulent. And you know, that's what I'm interested in. But they also up here, and I have other papers that I could do a better job of explaining. There is a period of maybe 2 or 3 hours. It depends on the weather patterns. If there's no fronts coming through, you can get a quasi-equilibrium boundary layer for maybe 2 or 3 hours in the afternoon. And you need that kind of time to do reasonable statistics and so on. Whereas the nighttime boundary layer, it's pretty much non-equilibrium all night. And it's very non-equilibrium around sunrise and sunset. So I was trying to make this point earlier. One has to be a little bit careful. We are doing this analysis for canonical equilibrium boundary layer with heating that corresponds to the early morning when the boundary layer is very much not an equilibrium boundary layer. Having said that, we have done some we are doing additional research, and we're trying to figure out how to get this written up and so on, that involves the non-equilibrium characteristics of the boundary layer in the morning period here. And they are strong. It's not, yeah.
Yeah, you're going from the neutral case to the midday, let's say from sunrise to midday.
Right. Yeah, this is a non-equilibrium period, especially in the early morning. I did a sabbatical at NREL once some years ago. And at NREL, when you walk in the National Wind Technology Center, when you walk in the door, they have a screen that shows in real time the temperature and velocity fluctuations and so on a Met tower that's outside. And every morning I would stand there and look and watch the transition from the nighttime to the daytime. And it's really dramatic. It's you can see it visually. Everything changes when the sun comes up.
Thank you.
Okay, so I think we have another questions in queue. So please, yeah, feel free to.
Hello.
Yes, hi.
Hi. Thank you very much for such a nice talk. It was really interesting.
Thank you.
I just wanted to know that the integral scales, the scales what you presented, L11, 1. I just wanted to know that are those? I think those must be the integral scales you have computed in the streamwise direction, and then you have taken the average over the span-wise to get a single value.
Oh, well, this is horizontally homogeneous boundary layer. So one of the advantages of doing horizontal homogeneous simulations is that you can use ensemble averaging over the horizontal plane to calculate your statistics. So you can either use time if it's stationary, or you can use horizontal direction. So we calculate these statistics by integrating in the horizontal plane and also over time.
Okay. Okay, and one more question I have, that is, if you can go to the slide which you skipped during the presentation.
Okay.
I think that slide before the summary one.
Yeah, it's this one.
Yeah, I was just wondering that if it's if it's a neutral boundary layer, that is at the minus Zi by L equals to 0,
right.
wouldn't we expect the U prime, W prime values to be the largest there?
The Reynolds stress.
Yeah. I mean,
well,
I was
yeah.
just wondering. I was just wondering why the values are increasing, because it would seem that the values should be maximum at
yeah. Well, I mean, you raise a really interesting question that's related to what I've been saying. How is it that the horizontal length of the streaks doubles, and how is it that the vertical velocity fluctuations amalgamate but do not grow in the vertical direction? They amalgamate in the horizontal. So yeah, you ask a good question. Is that related to the increase in the Reynolds stress? Maybe, it probably is.
Okay.
But I hadn't really, we hadn't really studied that question though, but it is a good question, yeah.
Okay, yeah, I think just if I add more to what Giovanni asked, it would be really interesting to see that if there is any change in the statistics of the ejection and sweep motions with this parameter Zi by L between these numbers.
I agree. Now, if somebody will raise their hand and say they would like to work on this, that would be great.
Thank you very much.
Actually, as I was saying before, this increase in Reynolds stress could be caused by an increase of anti-correlation between temperature fluctuations and the streamwise velocity.
Right.
Anti-correlation.
Right. Yeah.
Sorry,
yeah. Really good point. Yeah, absolutely.
Can I ask a question related to the correlations?
Yeah.
Hi, it was a very nice talk, so thanks a lot. I was wondering if you have any information, if you did any statistics about spectral energy, to know where is the peak in the spanwise direction. If I understand well, when you have streaks, so you have some spanwise wavelength on average, where energy is produced and so on.
Yeah,
like H, and then you have a transition to something with a larger spanwise scale.
Yeah.
So you see that in
Yeah, we didn't look at any spectra. Honest, we did do a lot more analysis than what I presented and what is in the paper. We were really sort of fixated on this coherence structure of the boundary layer. And we did do a lot more analysis that we had to remove from the first version of the paper because the reviewer said it was too long. Having said that, though, I mean, everybody is pointing out that it's a really interesting result, and there needs to be a lot more work done to figure it out. And you're same thing. So yes, no, we haven't done it, but it would be obviously a valuable thing to do.
Okay.
One I will say though about the horizontal correlation lengths of the streamwise fluctuations, that's the streak structure, right? So we have visual representations in pictures like this, where you identify the streak structure visually, and the point that I was making earlier is that if you compare the neutral state, this state, with the critical state, the coherence lengths of the horizontal fluctuations has actually increased in the horizontal. So that should show up in the spectrum clearly, right? The peak should move to lower wave numbers, for example. But what about the rest of the spectrum? And that's your point, and that's a very good point.
Okay, thanks.
So are there any more questions? Once again, feel free to unmute your mic if you want to ask a question, or you can even write it in the discussion, in the chat.
I think we're down to, sorry.
Can I
hello.
ask a quick? Sorry, go ahead.
Please.
Hello. Thank you for the talk. It was very interesting. I was simply thinking about the boundary condition, because when you have an imposed flux, then you can have no fluctuations at the boundary, at the ground. And would you think that it would be relevant to have some kind of heat exchange coefficient, maybe? So you can have both fluctuations of temperature and heat flux at the ground.
Well, we do have fluctuations in temperature at the ground. Obviously, the vertical velocity is zero at the ground because it's impermeable. The boundary condition is for heat flux. So when you do simulations, you have to provide a lower boundary condition. You could provide a temperature boundary condition or a heat flux boundary condition. And almost everybody universally provides a heat flux boundary condition, mainly because that's the more physical one. So that is the boundary condition. And I don't think it would make sense to add a separate model if that's what you're suggesting near the surface. I mean, it's the boundary condition. It's calculated, it's giving the physical result. Adding another model in, I think, would reduce the physical accuracy of it, if I'm understanding you correctly.
Yeah, I understand. And also maybe the key processes are not exactly at the ground and are happening slightly above. So the boundary condition might not be so important.
Yeah, and actually that's a good point. And that's kind of shown in this picture right here. Vertical velocity is really near the surface because it's suppressed. It's zero at the surface. Buoyancy-driven motions are strongest in the mixed layer. Shear-driven motions are strongest in the surface layer. And that's part of what makes this so fascinating. If you look at these pictures right here, the isocontour pictures are in the surface layer. They're at 0.1. Whereas these red dots and so on are primarily in the mixed layer. They're in these regions up here. So it looks like they're on top of each other, but they're really not. The red fluctuations are above the blue fluctuations. It's layered. The boundary layer is layered in these regions. And that's why the vertical communication is so important. That's why the fact that there was not vertical communication established until after the critical state is so important. Is so that the dynamics near the ground can communicate with the dynamics in the mixed layer and at the upper part of the boundary layer. That is part of what's interesting about this boundary layer.
Yeah, thank you very much.
Jean-Philippe, I think you want to ask a question, right?
Yes, just a quick question. Thank you very much for the very interesting talk. I was wondering how fast you increase your heat flux actually, and does it matter in the definition of the critical points? So do you just mimic the realistic case, or is it an issue actually in your simulation?
Yeah, so since these are the equilibrium states, we're analyzing the equilibrium states. When you start the simulation off, you just simply apply the lower boundary condition on surface heat flux and let the boundary layer evolve until it arrives at an equilibrium state. Now we have ways of deciding when the equilibrium state has arrived. It involves looking at statistics and non-dimensional variables and so on. So, and again, this is something that's been done for a long time, so we understand how to do that. But there's no time evolution involved in it. You just fix the heat flux at the ground and wait until the boundary layer becomes an equilibrium boundary layer, and then we collect the statistics from that boundary layer.
Okay, thank you very
much. Any more questions?
May I have one curiosity, maybe?
Yeah, go ahead, Francesco.
Yes, if I'm not wrong, your domain height is about something like 2,000 meters or so.
That's right. That's right.
Do you expect non-Overbeck-Boussinesq effects to be somehow interesting or relevant for your case? In particular, the dependence of density on pressure?
Yeah. So again, this is an issue that's been, these kind of simulations go back to the 80s. So they've been done for several decades now, and that issue has been looked at, and it's the reason why Boussinesq was argued from the very beginning as to be a reasonable approximation within the boundary layer itself. Mm-hmm. Obviously, if you go into the to the upper troposphere, so if I bring this picture up here, so we're talking about this very thin layer down at the ground, but if you go up into the upper troposphere, then yeah, you've got to get rid of the Boussinesq approximation. Mm-hmm. But in this layer, the changes in density and pressure are small enough that you can neglect non-Boussinesq effects.
Okay, thanks.
Some more questions?
Hello.
Hello.
Yeah, go ahead.
Hi. Well, first, thank you very much for your talk, which was very interesting, first of all. You mentioned a couple of times that you had great interest on the underlying mechanism, which you then completely understand.
Right.
And apparently there is some interactions between the mechanisms from a convective flow and from the strakes and rolls in a turbulent boundary layer. Well, there is some data processing tools like stability analysis or resolvent analysis, which precisely try to identify either from the equations or from raw data causality in these complex phenomena. And have you tried to, and actually they were used in the 90s to identify this roll streak cycle of the neutral boundary layer. Did you do any analysis in that regard?
Well, the answer is no, but I'm not totally sure which studies you're referring to. Could you maybe elaborate a little bit?
Yeah. Well, some years ago, the stability analysis of the equations, you know how you extract the eigenvalues from your problem and you identified what would be amplified. And there is a more recent upgraded version of it called resolvent analysis, which can also be done just from pure data from the simulations. You don't even need to rely on the equations, and they can be used at least from what I know, it's at least in the case of the boundary layer, to identify the self-sustaining cycle of the strakes and rocks.
Right. So the answer is no. I would love to have a theoretician, who understands how to do those kinds of stability analysis with modern tools. Say this is a fascinating problem. I'd like to work on it, and I actually have funding to work on it, which is a big issue. And I'd be interested in sort of keeping in touch with you to sort of let you know what I'm doing, and maybe get some interaction with you. I would love to find such an individual. Are you such an individual?
No, well, I'm interesting. I'm a student, a master student here in the LMFL. So well, maybe we can exchange.
Yeah, I mean, I don't have the resources to go any farther with this right now. This project ended a few years ago, and we're finally getting it published. But I don't have any resources. I don't have a student or postdoc that I could put on to doing additional analysis right now. So as you well know, you're a student. You're on the other end, but you have to have funding for people like you to develop studies and so on. And so this study is pretty much done as it is right now. Yeah.
Okay. Well, if you had any interest in for some other time on these sort of tools, I could.
Oh, absolutely. Yeah, absolutely.
Fit you some.
Yeah.
Thank you.
Thank you.
If I would like to, if it's fine with you, I would like to ask a very last question, and then we can close the seminar if that's.
Yes. Okay. Thanks,
okay. So in one of the plots you showed before, where there was the correlation of where there was a very clear identification of the length of the transition. Actually, there were clear length scales involved in. Yeah, that's it. That's one of this. Yes. There are actually clear length scales involved in the problems, which very well somehow correlates with the length scales used when designing wind turbines with horizontal axis. That's more or less what you showed at the very beginning as motivation, also part of motivations for your studies. And basically what you see is that like horizontal axis turbines, they are like, they have a height of the order of 100 meters or something like that. So they very well fall within the region of your graph where huge change is happening, and that's basically the novelty of one of the biggest novelties of the study. So do you think that this can have an impact on the design of a wind farm? Like how far should you, for example, position your turbines or your wind, sorry,
the wind turbines,
to avoid interactions, or to design a wind turbine without having to consider the interactions between them? Or
yes, I absolutely think it's important for those kinds of questions. In fact, that was the initial motivation, frankly. So if you do wind energy research, you know that some of the hot topics right now include the interaction between upstream wind turbines and downstream wind turbines through the wake. So one of the big issues is the evolution of the wake, and the evolution of the wake, it's already well known that the evolution of the wake is very different at night than it is in day, partly because the turbulent fluctuation level is much lower at night than it is during the day. These coherent structures, however, have a really important, I think anyway, I don't think anybody's really studied this in detail, but I think they have a really important impact on what's called meandering of the wake. So you get these coherent wake structures coming from behind the wind turbine, and they meander in the lateral direction. That meandering is really important to the function of the downstream wind turbines because they pass over those wind turbines. And one thing that is generally studied is how the momentum deficit due to those wakes impacts the loss of power at downstream wind turbines and so on. That's sort of like what people are studying right now. But people are waking up to the non-steady impacts of these motions as well. And that's actually an area that I focus on, is the non-steady impacts on the wind turbine itself. And I think that the meandering even though I would like to get into those kind of studies someday, we're still focusing on interaction between atmospheric boundary layer turbulence and wind turbines, say at the front of a wind farm. But I would really like to get into a study in which we study the impacts of these meandering wakes on the non-steady fluctuations on the wind turbine, because what happens is these non-steady fluctuations generate loadings that pass all the way through the wind turbine and have a really substantial impact. In fact, I'm involved in a project right now where we're trying to prove what I'm just about to say, that have a really strong impact on breakdown of components on the drivetrain, in particular the main bearing and the gearbox bearings and so on. I feel that the wind turbine operating in the middle of the day is experiencing different non-steady loadings than at the beginning of the day or at nighttime and so on, and that these differences have an impact on the function of the components that can accumulate and lead to early breakdown. It's well known that the gearbox breaks down earlier than it's supposed to. The main bearing breaks down earlier than it's, and I've been arguing for a long time, based on some of the work that's come out of my earlier groups, that the bearing failures are largely a result of this wind turbine turbulence interaction. So I think the answer is yes, although there's a lot of work that needs to be done to verify what I just said.
I see. That was a very interesting talk. So thanks once again for giving a seminar here at LMFL webinars, and I invite everyone to thank our speaker once again. Thank you, Jim, for the very interesting talk.
Thank you very much, and I look forward to meeting you all when I come out.
Yes. All
right. Thank you.
Thanks again, and I hope to see you all next time, and a good evening or a good day, depending on where you are. A good evening. Bye.
All right. Thank you.